Good evening, everyone. Welcome back to our webinar series on quantum algorithm using Qniverse. Last week on Wednesday, we had with us Mr. Henry Sukumar, who walked us through Qniverse and its features and capabilities. Many were asking in the webinar that to conduct this webinar series little late, around 6. So this intermediate session we have made at 5:30 to 6:30, and since next webinar on Wednesday, we will be starting with the actual algorithms. So in between, many were asking the basics of quantum qubits and gates. So this week we thought, okay, we will start with the qubits and gates, which is the building blocks of quantum computing. So this week, this intermediate session, we have with us Dr. Naresh, who is from C-DAC. He has his MSc from physics, MSc in physics from University of Hyderabad, and a PhD from National University of Singapore. His research area was on quantum computing. He brings 11 years of expertise, and his research focus spans across quantum computation, cryptography, topological phases of matter. And at C-DAC, he is involved in various projects like quantum network simulator, developing quantum network simulator, even in fact the Qniverse. And he is the brain behind developing the algorithms in Qniverse. So, with this, I request Dr. Naresh to give this lecture. Thank you.
Good evening, everyone. Am I audible? Thank you. I'll just share my screen. I hope the screen is visible. Yes. Okay. Today, before we are going into the other algorithms, right? We thought we'll have some session where we'll talk about the basic building blocks of quantum computing. Now, the basic building blocks of the classical computing are bits, right? The underlying mathematics is a Boolean logic. Now, going to the quantum computing, the basic building block is qubits or quantum bits. Okay. Um, Now, let me explain first abstractly about what is a qubit. A qubit, it's actually a state of a qubit, is a unit vector in a two-dimensional complex vector space. So basically, it's called as an Hilbert space, where the inner product between the vectors in the vector space are defined for a pair of elements. Okay. Now, if you look at this here, a qubit could be a superposition of its bases here. So in this case, this notation is called a Dirac notation. So where there's a bracket kind of thing, line and an arrow mark. So this is a Dirac notation, and it's called a ket here. So it's a ket 0 and ket 1. So the alpha and betas are called probability amplitudes. Okay, so they are actually a complex numbers, and the condition for them is that so the normalization of alpha and beta, which is modulus alpha square plus modulus beta square, should be 1. Okay. Now, let us assume for a time being alpha and beta are real numbers. Okay. So if you look at here, so if it is, this is in two-dimensional plane, where if in the case of alpha and beta are real numbers, we can actually look at, yes. So the state psi, right? Now this is the projection on this one. So this is alpha and this is beta. Okay, so modulus alpha square plus modulus beta square is equal to 1. So let us take this as theta. As I told you, if it in the case is alpha and beta are real numbers, we can see this as alpha can be thought of as cos theta, beta can be thought as sin theta. Okay, but as I mentioned to you, alpha and beta are not real numbers. It need not be real numbers. Okay, so they can be real, but need not be always. So they can be complex numbers. So for complex numbers, what we can do is that, you see, I'll just try to represent the state. Psi is equal to, as I mentioned to you, alpha 0 plus beta 1. Now, if alpha is a complex number and beta is a complex number, we can write this as R1 ei theta 1 0 plus R2 e power I theta 2 1. Now, if you look at this point, right, now we require 4 parameters to define a qubit. That is where now we'll simplify it. You see, now one of the condition is that modulus of alpha square plus modulus beta square should be 1. So that means that what we turn it out to be R1 square plus R2 square is equal to 1. Why is that? When you take the complex conjugate of e power I theta 1, so that will get cancelled with the plus and the minus part. So you have this is the one equation. Okay. Okay. Now the other equation, what I want to say here is that now let me define theta 2 is equal to theta 1 plus phi. Okay. So that turns to be then now from this condition, what I will do is that I will write psi as from both these parameters. R1 I can write in terms of cos theta by 2. Okay. Cos theta by 2 e power I theta 1 plus ket 0 plus R2 is e power sin theta by 2 and e power I phi. Okay, 1. What I will do is that I will just take e power I theta 1 outside. Yes. So you see, this e power I theta 1 is a global phase for a qubit, right? When you're talking about a quantum state, so this global phase will not matter. Okay, so in turn, this we can write it as so finally it turns to be that we require two parameters. One is a theta, another one is a phi to define a qubit. Okay. Now, one way of visualizing the qubit is like this one, as I told you, in terms of a Bloch sphere. So what's a Bloch sphere is that now this is a state which I'm talking about, right? Now theta can take the parameters of from 0 to pi. The value can be from 0 to pi, and phi can we go from 0 to 2 pi. Okay. Now, any qubit can be represented as a Bloch sphere. So there is a one-to-one mapping between a qubit and the representation like this one. So this is a Bloch vector. Okay. If you look at here, it's a one-to-one correspondence. So basically, we require a two parameters, theta and phi. Okay. So the qubit can be basically we're talking about a pure states here. So the qubit will be on the surface. Okay. So now let us take ket 0. Okay, so let us talk about the ket 0. Now ket 0 is when theta is equal to pi by 2 and theta is equal to pi. That is for 1. So when for 0, ket 0, theta is equal to 0, right? So that turns to be then it will be on the north pole of this Bloch sphere. For the 1, theta is pi. So that is cos pi by 2 is 0. So then it turns to be the global phase of e power phi, and it will be in the south pole. Okay. So we can represent any single qubit on this Bloch sphere. Okay. So this is the one way of visualizing the single qubit states. Now, when we're looking at the literature, right, you will find out the Bloch sphere. So this is how we need to look at this single qubit state. Okay. Now, the interesting thing about the qubits, as I told you, it will be in an superposition of ket zeros, ket 1. Now, if you want to talk an equal superposition between a ket 0 and ket 1, so our state is 1 by root 2, 0 plus 1. Okay. Now, that is the state, it is on the x-axis. How do you get that? Now, just place the variable here. Now, theta is equal to pi by 2. Okay, so it's a cos pi by 4. It comes to the 1 by root 2 ket 0, and sine pi by 4 is 1 by root 2. So it will be on the x-axis. So in this way, right, any kind of a state. So when you varying the parameters of alpha and beta, okay, if you look at here, the theta is an angle between the z-axis and the block vector, whereas the phi is an azimuthal angle here. Okay, in this way, we can represent any kind of a qubit state on a Bloch sphere. But the it's not so advantageous is that for a multi-qubit states, we don't have this kind of representations. Okay? This is only for a single qubit where we can visualize the things. Yes. Now we are talking about abstractly, but to do calculations bit easier and make our life simple, right? So we can represent the state, the qubit, in terms of vectors. Okay, so how can we do that? So let us take that the basis states ket 0. So we can define it as this vector as a 1 0. Okay, and ket 1 as 0 1. So if you have a qubit psi alpha 0 plus beta 1, so it turns to be that in the vectors it is nothing but alpha and beta. Okay, we already know that modulus of alpha square plus modulus beta square is equal to 1. So any kind of a qubit can be represented in terms of a vector, okay, because it's a superposition of ket 0 and ket 1. So, but now you see, we are talking in terms of a mathematically. But here's one of the famous quote by Peirce, who says that you see, quantum phenomena do not occur in a Hilbert space, but they occur in a laboratory. Now, I think in the earlier talks read by Professor Apurva Patel and Mr. Henry, they mentioned that you see, physically a qubit is an can be in quantum particle, such as a polarization of the photon. It can be a nuclear spin. It can be an atom itself. Okay, so these are the real qubit systems. Okay, now the quantum computing, why do we require quantum computing? First of all, you see, quantum computing is based on the governing principles of quantum mechanics. So we take the advantage of the quantum mechanical principles to do the computing. So that's why it's known as the quantum computing. Okay. Now going forward, you see, we have a state here. Now I mentioned to you that's a qubit for us. Okay, it's a basic building block. Now we need to do some kind of operations on the qubit. Okay, I will talk about the gates here. So what kind of operations are allowed on these qubit states? Okay. So again, as I told you, the governing principles are the quantum mechanical principles. So now let us take, you have an initial system. Let's take state psi1 or a qubit psi1 at time t1. Okay, now after time t2, you want to find what is the state. So basically, we need to find what is the operation has been happened between t1 and t2. Okay, if we apply some kind of an operator, okay, the operator, so not all operations are allowed. So only those operations called unitary operations. Okay, what are the unitary operations? So basically, you have an initial state psi1. Now you're applying in unitary operation on u, a unitary operator u on psi1 to get a psi2. So this unitary operator is nothing but this one. U dagger U is equal to identity. So basically, if you take a, let us take in terms of matrix, because we just introduced a vector. So we're talking about a qubits here. So let us, U is an 2 by 2 matrix. Okay. A, B, C, D. Okay. Now what is U dagger? U dagger is, you take a complex conjugate of that and transpose this. Yeah. So this is the U dagger. Now, so your operation, unitary operation should be that U dagger should be identity. And U dagger use in turns identity. So only these kind of operations are allowed to do in computing, quantum computing here. Okay. Now, some of these are well-known gates. Maybe some of you have been already went through some of these gates. You see, if you look at this is a NOT operation. So NOT operation, so it's called Pauli-X, Pauli-Z and Pauli-Y. So this X gate, it's like a NOT operation. When you act on 0, it flips the qubit state to 1. And it acts on the 1, it flips to 0. Now when Pauli-Z acts on 0, nothing will happen to the state, but acts on the 1, you have a phase, you have an additional phase of -1 here. If you look at here, if you want to represent in terms of matrices, so X is nothing but 0, 1, 1, 0. Okay, I told you. So when it is acting on 1, 0, it turns out to be 0, 1. Okay. Now this is, as I told you, right? This is how the matrix will help us in solving these problems. Okay, so in a simpler way. So this is how X gate. Similarly with the Z gate, right? Now you have Z gate will be 1, 0, 0, -1. If you look at here, so this will give an additional phase to the Ket 1. Okay, and we have one more operation Hadamard here. Okay, now earlier we introduced the Bloch Sphere. In terms of the Bloch Sphere, you can see that, you see, your Ket 0 will be on the north pole and Ket 1 will be on the south pole. So if you're operating X gate, so what it does is that, so this is an X axis, this is the Y axis, and this is Z axis. So when you operate an X axis, so when you operate an X gate, so what it does is that it rotates the state pi by pi around the X axis. Okay, so that what is this? Is this Ket 0 becomes the 1 and Ket 1 becomes 0. And any kind of a state can be, you see, you can. So if you look at here, X acting on any kind of a psi. Okay, so your psi is alpha 0 plus beta 1. So what it does is that when you operate on this kind of states, so it flips the state to alpha 1 plus beta 0. Okay. Similarly with the Z gate, what it does is that it rotates the qubit around the Z axis by pi rotation. Okay. Yes. So when Z acts on the 1, so it adds an additional phase of -1, at a phase of -1. Okay. Now here, right now we are talking about circuit model in this particular webinar series. This is the circuit model of computation. Okay. Now till this point, we spoke about the initial states, which is the qubit representation here. Q0 and Q1 are the qubits, and these are the gate operations. So this is the Hadamard operation, and this is the CNOT operation, which I didn't interest. I will speak about in a minute. This is a multi-qubit operation here. It's a two-qubit operation. Okay. Now, how do we read this thing? Okay. Basically, right, a quantum circuit. So we have an initial inputs as the qubits. Okay, and this is a classical register. I'll come to the classical register. So it's connected by straight lines. So which indicates the direction of the how the logical flow is flowing with the time. So how the logic is flowing with the time. So earlier time being the left, and the right being the forward time. Okay, and these are the measurement operators. Okay, if you want to read the state, we need to measure the state. Okay, So, and measuring the states will be the classical, it will be captured in the classical registers. That's why it's a C represented here, and this is the classical bits here. Okay. I'm just speaking about the quantum measurement. Okay. Now, what we spoke till point, at this point, we spoke about initials, the qubits, and then we spoke about these time evolution of the qubits. How do we operate on the qubits? Okay. This is for a closed system. Okay. For a closed system, you have to be working with the unitary operations. Okay. Now, coming to this measurement, right? Now, if you want to read an any kind of an qubit, finally you have to measure it. So that's how we capture the information from the qubit. Okay. Now this is the qubit. Okay, it's in a superposition of ket 0 and ket 1. Now for this point, for this webinar series, right, we are restricting ourselves to standard basis measurement.
Measure information from cubes. You can consider
Sorry.
aspects like the number of distinct.
Yes. So here, right now, once you measure the state, as I told you, we are measuring the standard basis measurement. So we're measuring finally in the ket zeros or ket 1 here. So when we measure the state, so we have a probability of modulus of alpha square of getting 0 state. Okay, modulus of beta square of getting 1. Okay, now this is how the quantum world works. Now, but you see the another important point here is that once you measure the qubit, so the state will be always in that particular state. So in this case, let us say that you have a qubit like this one, and you measure the state, and you got the result as ket 0, and subsequently the state will be in the ket 0 itself. Okay. Similarly, the case with the ket 1. So that is how the quantum measurement will work in the quantum world. So this is a symbol. So this is a measurement symbol. You're seeing here the black here. So that is the measurement thing in you will see in the Qniverse. Okay. Now from single qubits, right? Let us go to the two qubits. So we have a psi 1. Okay. We have 1 qubit, alpha 1 0 plus beta 1 0. Sorry. Beta. There is one more qubit, psi 2, alpha 2 0 plus beta 2 1. Okay. Now this is a composite system of two qubits. Now the total state, if you consider the single system, right, your total state, let us call that capital psi. Okay, the capital psi can have 4 states. Okay, let me call this as alpha 0 0 0 0. So this is a new probability amplitudes, alpha 0 1 0 1 plus alpha 1 0 plus 1 0 plus alpha 1 1. So we can have a superposition of all the 4 states. Okay, so 0 0 0 1 1 0 and 1 1. Okay, so this is the composite system here. Now there is an interesting state which you might heard in the first 2 lectures about an entangled. So this is one particular maximal entangled state. You see, you can actually decompose this state into back to individual states. But if you look at this particular state, right, psi is equal to, let us take that so 1 by root 2 okay, so this is a state. Now we can't actually decompose this particular state into product of these two kind of states. So this is called an maximally entangled state or a Bell state. So this is one of the Bell states. Okay, so this is called an entangled state. Okay? So which is one of the essential according to Schrodinger, he says that this is a characteristic feature of the quantum mechanics. So in turn, it will be a characteristic feature for quantum computing as well. Okay. Now for this kind of multi-qubits, right? Multi-qubits, we can have a multi-qubit gate operations. So we saw this as earlier single qubit gates. So this particular is an superposition gate. Okay, where when Hadamard acts on 0, it will gives an superposition of equal superposition of zeros and 1. So this is called an Hadamard gate. So this kind of an gate operation which gives into the superposition state. Similarly, there is a C-NOT gate. Okay, so this is a two-qubit operation where the black dot represents the control and this is called the target. What does this do is that, so when your control qubit is 1, it flips the target state. Okay, that is what you can see here. Okay, in the standard basis of zeros and 1, you can write in terms of a matrix form here. So this form, which is a 4x4 matrix. So if you look at here, right, when it operates on, say, on the state like something like 0, 0, 1, 0. Okay, so you can see that how does this act. So basically, it flips the state when the control state is 1. It actually flips the target state here. Okay, so this is how we can actually represent in terms of a matrix form. Okay. Yes. Now, as I told you, these are the earlier I spoke about this particular Bell state. So there are 3 more Bell states. So these are maximally entangled. Okay, what's a maximally entangled? So just to say that, right now, earlier we have seen that measurement. Now there are 2 qubits. So one of the qubit, so there are 2 qubits here. So if you measure the first qubit, so what is the probability of getting the 0 for the first qubit? Okay, for this particular state. So we'll consider it for this time being for about this state. So what is the probability of getting in 0? So basically it has a probability of having 1 by root 2, right? So it's a probability number of 1 by root 2. It's a modulus square is 1 by 2. So it is the probability of getting 1 by 2. So once you measure the first qubit, okay, it has an equal probability of getting a zeros and 1. But once you got that particular state, so for example, in this case, let us say that we got a 0. So instantaneously, the second state will also be collapsed into the 0. So if the first state is 0, the second state will also be 0. So let me write this as, basically this is a tensor product. So that's basically is a tensor product state. So we are writing for a case like this one. Okay. So now once you measure the particular state, right, in 0, so the other state will also be in a 0. Same thing with the 1. So if the first state it turns to be the 1, the second state will also be 1. So as I mentioned earlier, subsequently the state will be, both the states will be collapsed to either this one or 1, 1. Now this is what is an entanglement. So entanglement, right, as I mentioned earlier, you can't decompose it into the product states. Okay, it's a complete system here which can't be decomposed into the product states of each individual qubits. Okay. Okay, I think at this point, right, so basically to revise what I mentioned. So basically there's the building blocks. Initially we started with the single qubit state representation. Okay, then we spoke about the time evolution of the state, the qubits, and then what about the measurement? Okay, so then we went to the vector representation, okay, of these qubits and the gates, and subsequently we spoke about the two qubits. So it could be generalized to the multi qubits. Okay, now in the gates, right, the quantum gates, now basically we can have in some universal gates. Say for example, when you're talking about a multi-qubit states, okay, one essential qubits you require is in, say, you require in superposition, okay, which is an important characteristic of the quantum computing. So you require an Hadamard kind of an gate, okay, and phase gate, okay, and you require an, when you have a multi-qubits, you require an qubit which interacts the qubits. So in this case, the C-NOT could be useful as an gate. So Hadamard phase and the C-NOT could be one universal set of gates. So you can have multi universal set of gates, okay. But when you're talking about the multi-qubits, you definitely require a gate which correlates the two qubits. Okay, so that is one essential point we have to remember. Okay, so with this thing, right, I will stop the mathematical representation and I will go to the Qniverse to just to demonstrate what we have learned today. Okay, maybe I think before leaving, right? You see here, you can actually prepare a Bell state using Hadamard and CNOT operation. Okay, so the Hadamard operation, right? So it makes the first qubit in superposition. Okay, like this one, like this, and then you have the second qubit in the 0. Now you're operating on a CNOT gate. So basically, what it does is that now CNOT gates, the first qubit, if it's a control, it will not do anything. So it will be 0, 0, root, okay, plus the first qubit is on the 1. Okay, so it flips the second qubit. So it becomes a 1, 1. So this is how you can make one of the Bell states. So similarly, if you want to make another Bell state, right, you can have the same operation, Hadamard and CNOT operation. Then you require an minus phase before the 1. So you can operate a jet on the qubit 1 here. Okay, so that you can get a 5 minus. Subsequently, similarly, you can get other Bell states. Okay, so now we'll shift to the Qniverse. So before that, if anyone have any questions, right, I will be able to answer.
Muted.
Yes.
Thank you, Naresh. There are few questions asked in the chat box. Gursimranjit Singh, he asked why theta is traversing only 180 degrees and phi 360 degrees.
Okay. Okay. Am I audible? Yes. If you look at here right now, we have taken cos theta by 2. Okay. So that is the reason we have a limit on the theta. And also this sphere, right? The Bloch sphere is actually the double cover of the normal sphere. So that's why there will be a limitation on the theta. Yes.
Mute. Yeah, the next question is Harshit asked, when we are taking a phase gate, how do we determine which direction, clockwise or anti-clockwise, does it swing the qubit on the Bloch sphere?
See, oh, yeah. Now, in the Bloch sphere, right, generally we represent it as a clockwise, but that is a notation we can follow. Okay. Now, if you define how do your Bloch sphere works, right, it can go in the anti-clockwise also, but general convention is a clockwise.
The next question is by Chanchal. What does this circuit represents? The algorithm or the process at each time?
So, as of now, right, we have not spoken about any algorithm at all, but this is a process itself. For any kind of algorithm, this is a building block. So, this is how you need to construct the circuit. Okay.
Yeah. Next question is by Nikhil. Why are Bell states useful in quantum teleportation and cryptography?
Yeah. So you see, as I told you, right, the two main essential characteristics of the quantum computing. One is the superposition, other one is the computing. Okay. If you talk about a Grover's algorithm, right, you can actually see how superposition plays a huge role. And the other important characteristic, which is entanglement. See, entanglement, what it does is that, as I mentioned to you, it is a special characteristic, okay, where you have a correlation between the two qubits. So, especially you ask about this quantum cryptography. Now, you can actually, so there are various protocols. So, something like E91, Ether Accord protocol, which is developed in 91. So, where they use this Bell states. Okay, so you can actually, these Bell states can be useful to see whether their eavesdropper will be intermediately eavesdropping the communication. Okay, maybe that in subsequent webinars, right, you will be able to see that. Yes.
Yeah, the next question is by Dilip. I am very confused with measurement, observable, and so And the other question he asked is in between unitary operation and Hermitian in circuit level.
Can you repeat the second question?
Something he's bit confused on unitary operation and Hermitian in circuit level.
Okay, you see, maybe I lost the answer the first question, sir. Second question first. You see, unitary operation is where, how do you operate on the your qubits? Okay, whereas a Hermitian, Hermitian is something, you see, you can, you see, physically, how do you say is that you require Hermitian operators, but okay, let me try to answer it in a different way. Mm. Given an Hermitian operator, you can build an unitary operator. Okay, but a real physical observable, right? That's the first question you are asking. You see, any physical observable, we need to operate using a Hermitian operator. Maybe that's the thing, right? I think I didn't cover that aspect in this particular lecture. But how do you say is that? You see, if you want to do a measurement, basically you have to know which kind of an observable you are actually want to measure. Okay, so your observable decides which kind of a basis you actually look into. So that is how, in a sense, right, the observables will come into the play. Subsequently, Hermitian operator will come into play. So basically, I'm not sure how much uh, you can understand at this point. You see, but see, for example, when you have a Hermitian operator, right, you have in this eigenvectors. Okay, so basically, in general, the eigenvectors will be your observables. Okay, sorry, observables. So that the eigenvalues will be the whatever you observe. Okay, I hope I answered your question, but this is how it works. Okay.
Yeah, we will move on to the further demonstration.
Okay. Fine. So can I answer that? What is the observable versus measurement, right? Yes. So to just to say, right, so for example, in this case, so I will just tell physically, you see, you want to measure a spin. So basically, what are the ket zeros and ket ones? So as I told you, it could be a physical quantum particles. Okay. So for example, it could be a polarization of the photons, or say, for example, electron spin itself. You can have an, say, spin up is a ket zero and spin one, spin down is ket one. Okay. Now, you have to say that, okay, in which kind of basis I want to measure. What is that? Now spin up and spin down, let us say it's a jet basis, but you can also have left and right. Okay, so you can choose, okay, I want to measure the spin up or spin down. So in that sense, so you are actually measuring the spin up and spin down. Okay, so this will be an your observable. Okay, so this is what how it relates to the measurement. Okay, so that's why I told you when I'm talking about this in this case, right, in our webinar, we will constrain it to the one particular standard basis measurement. So we are constraining it to the Z basis. But if you want to measure X or Y, right, you can do that. Okay, using our Qniverse, you can do that. Thank you. I hope this will able to clarify your doubt. Okay, I think I can continue to the Qniverse. So whatever we discussed, right? So let us look into the Qniverse. So whatever we taught, we learned today, we can. Okay. Now here, right, in the Qniverse, we'll talk about first. We are talking about a single qubit. Sorry, I didn't share the screen. Yes, is it visible? Yes. Now first we'll talk about the single qubit. Single qubits. Okay. Okay. Now look at here. Now in the Qniverse, right, the initialization, if you're not doing any initialization, the state will be generally in the ket 0. Okay, you can see that here. So it will be in the 0. Now you can modify the state. Okay. Say for example, you can modify it to, yeah. So it's an ket 1 state. You can see here, so this is the probability distribution, and you can see here the state vector representation. So the state vector, it says that it is an ket 1 state. Okay, if you're doing a NOT operation, okay, so it comes to the 0. Okay, right? Now I apply a Hadamard gate so that we will get in superposition state. Okay, here if you look at here, right, now you're having n, you see, let me remove this. So if you add one more NOT gate, so we'll see what will happen. So basically now what is the state here is that you actually started with the ket 1 state, then you added a NOT gate. Okay, so it comes to be, so 1 turns to be 0, so you have an equal superposition of plus state. Now if I add one more NOT gate, okay, now what happens, it turns to be 1. So when I operate in a Hadamard gate, so what you're getting is in minus state. So basically in equal superposition, but it's a 1 by root 2 ket 0 minus 1. Okay, 1 by root 2 ket 1. That's why you're seeing the phase here. Okay, but if you look at the probability distribution, so this is what the probability distribution comes. Okay, now both of them will have the same kind of a probability distribution. Okay, yes. Similarly, having in say Z gate. I'll remove this one. So Z gate, when it acts on 0, okay, when it acts on 0, it's not doing anything. But let us act out on 1. You see, got a 1 and it got a phase here. So that's what the color shows here. Okay, so this is how you need to read the states. So we need to see the state vector representation to find out the phase, relative phase between the your bases here. Okay. Okay. Now, as I told you, this is a measurement operator here. Okay. So here we need to run to see what the state will turn out to be. Okay. And then let me add multi-qubit gate. So because there are 2 qubits, I want to see the what is the final state at the end of the my operation. So I need to have 2 measurement operators here. So you see here, that's a question asked, right? So this is what I'm doing in a Z basis. Okay, my observable is in the actually Pauli-Z here, the spin in the Z axis, in the Z direction. Okay, that's what the Z represent here. Okay, okay. Now to get in Bell state, right? So we have an Hadamard in the first state. So basically, let me go to the, you have a reset actually. So initially I started now ket 0, but then I modify it to ket 1. Now to get back to 0, right? One thing is that you can go to here and you can actually modify the state, or you can come to this one, reset gate. So if it is reset, right? Now whatever the operations, it will turn out to be 0. Okay. Now that is what the reset operation turns to. It is now we got a Hadamard here. Then we'll apply an control NOT gate to Bell state, which I have actually shown to you. You see here, it's a 0, 0 and 1, 1. Now you get to get a one more Bell state, you can actually add Z operation. Yeah, so you can see here, it's a 0, 0 minus 1, 1, so of equal superposition between them. So this is how you can actually see, you can play with, so as I told you, so this is the qubits, okay, and this is the operations, the unitary operations we are doing here, and then this is a measurement. Okay, right? So then finally, right, if you want to run your state, you can go to the CPUs or GPUs or the QPUs, and you can run subsequently here. Okay, I hope it should be fine. And here, right, I think Henry mentioned this point, but to just to repeat once again, right? Now this here, you can actually see when Hadamard acting, Okay, when Hadamard acting, so this is in a standard basis again. Okay, so in the standard basis, when I'm operating it on 0, okay, you get an equal superposition of zeros and 1. When at Hadamard gate acting on 1, you get an equal superposition. The size of this sphere, this circle, right? It is actually says that what is the probability amplitude. Okay, now for both of them, you have the same probability amplitude, but only thing is that it has a phase factor. Okay, so that is what it shows here. Yeah, I think this is a fine. Plus minus basis. Okay, so plus minus basis, right? As you the last person who asked about these observables, now you no need to measure always in the z basis, right? So as I told you, you can actually measure it in the x basis, okay, or you can measure in the y basis. So if you're measuring in the x basis, right? Now if you're measuring in a say you're measuring the plus state, okay, so a plus state will be so here it shows that Hadamard gate. So let me show you first of all Pauli-X gate, which is easy to work out here. Now you see here, now when you're talking about Z basis, when the 0 is input, it flips to the 1. But when 1 is the input, it flips to the output to the 0. Now here in the x basis, right, your plus and minus are actually the eigen vectors. Now that's the question when you're talking about the observables, right? Plus minus are the eigenvectors of Pauli-X basis. So when x is acting on plus, nothing will happen to the plus. Okay. When it is acting on the minus, it has the phase of minus. Okay. So that is how it is coming. But when it comes to the plus and minus I basis, so this is how it is working. Okay. Same thing with the Hadamard gate operations here. Okay. Now this is how when it is acting on a zeros and ones, and when shifted to the plus and minus basis. Now this is how it is acting. When the plus is input, okay, you have an equal probability of having plus and minus. Okay. When minus is input and when you're opting in a Hadamard gate, so it has an plus and minus as an equal output, but with a phase of -1. So this is how you can see this phase here to show to represent what is the phase here. So this sky blue color represents the pi phase, and the amplitude is 0.707. Yeah. Yeah. Thank you. I think with these things, right, I can stop here. If you have more questions, please feel to ask. Okay, I'm happy to answer. Thank you.
Naresh, thank you. There is one question by Muttamil. Is it possible to build a simple harmonic oscillator eigenvalue and eigenvector solving problems in Qniverse?
Sorry. Yes, we can actually build it, but the thing is that now we have to represent in terms of in qubits. You see, but you see, when you're talking about a qubit, right, it has only 2 levels. But in a harmonic oscillator, you have multiple levels. So in the Qniverse, you can only restrict to the 2-qubit system. Yeah.
Yes, thank you, Naresh. We have come to the end of this session. Thanks to Naresh for giving that insights on basic building blocks of quantum computing, that is qubits and gates. Yeah, few announcements. For last week, the Wednesday's webinar, we had posted a few quiz questions and even the question and answers which we could not able to take up during the session. So those question and answers are also being posted. You may watch it, and there is quiz questions we have posted in Zuli platform as well. So please take time and please attend those. And for this session, we will be posting the quiz questions by tomorrow. And please take your time to answer those questions. And for many were asking about the videos, the recorded one, and the materials. It's already been communicated over the email that the materials are already being posted through our GitHub channel. So you can go and visit, and you can use those materials. And for YouTube, the videos of the session, It's already been live and been shared through YouTube, our YouTube channel, that is Qniverse.in. So you can visit and you can watch anytime. And for those who are attending, not able to make it through the webinar, the WebEx platform, and who are coming through YouTube, so for them we have enabled a attendance system. As I told you in the last week, we are expecting a 75% attendance for you to qualify for getting a certificate of participation. So in that regard, those who are not able to attend, those who want to view the YouTube videos, for them we have given a link in the video, to register their attendance. So do please watch the video and place your attendance so that it can be marked and it can be used for our attendance system. Yeah, that's all for this the special intermediate session, and hope to see you back on Wednesday with another series of lecture by Professor Anirban Patak on quantum veto protocol. Thank you all. Have a nice day.